Hello, my name is Shivam Arya, and today I'll be presenting my AP research paper on investigating a method to increase the robustness of predictive steering control autonomous navigation systems against dashcam image angle perturbations due to pothole collisions. So let's get started. Today we'll be discussing the four major sections of my paper, which includes the introduction, where I'll preface the problem and review the lit review and the gap in the scholarly conversation surrounding my topic. I'll overview my method, which is the process I propose for solving the problem identified in my intro. I will go through my results, which will show my data that I obtained in the actual method section. And then I will overview my analysis and my conclusion, where I will go through my analysis and the implications of the results that I obtained in the third section. Let's start with the introduction. So the inspiration for this paper came from a few months ago, where we were driving down a highway in our car and we had autopilot engaged. And then as soon as the car hit over a pothole, we heard a loud bang and we had to pull over, and our tire had popped. And we realized that autopilot had not identified that there was a pothole and had gone full speed over a pothole on the highway. And then I realized that this was like a very dangerous problem. And so I started looking at the scholarly research surrounding this area, and I found that the average American drives 14,263 miles per year, which amounts to 3.2 trillion miles driven by Americans per year annually. And a direct impact of the pothole could result in the same effect as a 32-mile-per-hour collision, which could be lethal. $26 billion are spent by drivers on pothole repair per year, which is a huge industry. And 1 in 10 drivers must repair their car after hitting a pothole. So then, multiple researchers have actually identified this as a problem and have looked at ways to solve this problem. The first general category of solutions is the vibration-based approach, where authors will put accelerometers in a car and with other sensors to mathematically analyze the jerk induced when the car goes over the pothole. This is a very effective technique in identifying whenever the car goes over a pothole, because it can measure the car's reaction and what happens to the car. However, this cannot perform any predictive steering control, because the car does not know the pothole is there before it actually goes over the pothole. The next general approach is the depth-based approach, where the researchers use light, depth, and ranging sensors, or LiDAR sensors, to approximate the location of pavement anomalies before they happen, so that the car knows about the pothole before it happens and the distance in front of the car. However, the car does not know about the environment surrounding the car, and so it cannot make a solid decision in the navigation system of how to react to the pothole. The final general category of approaches is the GPS-based approach, where researchers consolidate data of a pothole on a central server. This is similar to in Google Maps, where you have the speed trap detection, where multiple users report the speed traps, and then they get sent out and propagated to all other users of the same Google Maps. And this is sort of like a crowdsourcing of the pothole data. However, this is not as effective, because this cannot have live updating information about the pothole. If the pothole gets filled in, or if a new pothole occurs, or if the pothole gets bigger, the central system will not know about it, and other cars will not know about it until one car first acts as a guinea pig and goes over that pothole. So this leads to the gap in this scholarly research. And the gap is that there's very little research on the post-impact effects on the actual autonomous navigation system. So what this means is that when the car is deciding where it wants to drive, it is using a camera input to see where the car's lane is, and then it's deciding the steering angle of the steering wheel to control where the car will go and how it will react. The research that I've looked at in this general area does not look at the effect of going over a pothole on this steering angle control of the autonomous navigation system. Because, for example, it could induce an image perturbation in the dash cam of the car. If the car goes over a pothole on only one side, then the dash cam could shift an angle. Or if the car goes over a deep pothole on both tires, it could translate downwards or upwards. And researchers have not looked at the effect that this has on the autonomous navigation system's response to the controlling the steering angle and keeping the car in its lane. So here is my proposed solution or my proposed method to analyze this problem. I will go through pothole generation, where I will create I'll create 3D models for a sample of potholes. I'll go through statistical analysis, where we will look at the average statistics for these 3D pothole samples that we have gathered. And then we will apply these statistics from the statistical analysis onto a real car to mock a simulation on what this effect will do on a real car. So let's start with the pothole generation. So for the pothole generation, I went online and I found this data set called Pothole 600, where researchers had gathered a set of 600 different potholes around their area. And these potholes consisted of 3 images for each pothole: a black and white label image, a red, green, and blue top-down view of the pothole, and a heat map, which is in the jet color scale used by MATLAB, the programming languages that the researchers use. This heat map is of the depth of the pothole at any area, and they calculated this by using ZED stereo cameras mounted at multiple angles in the car to figure out every point on the road in front of them. And they used this to gather all this data about the potholes. Now, what we can do, if we want to perform statistical analysis on this sample of potholes, it's easier to use something like this, which is a 3D image, or a 3D model of the pothole. This contains all data about what the top of the pothole looks like in any angle, and contains the depth of each section of the pothole at any point in time. Now, the question becomes, how do we turn these three images into a 3D model like this? To solve this problem, I looked towards a 3D modeling software called Blender. Blender is an open source animation and 3D modeling and sculpting software that let me combine these three images into a 3D model like this. However, it became very cumbersome and infeasible to perform this same operation for 600 different potholes. And so I discovered the Blender API, and I investigated the method of this API to connect the programming language Python with the 3D modeling software Blender. And then, using this API, I created a program that will allow me to recursively create 600 different 3D models for the potholes based on the three images given by the researchers, and place them all in one folder for easier statistical analysis. And this is an example of some of the code I used to do that. So then, for the actual statistical analysis, now that we have the folder of 600 different potholes, 3D potholes, we must perform statistical analysis on 3D objects. For this, we will split each pothole into a 10 by 10 grid of 100 different subsections. So there will be square-shaped subsections of 3D models of potholes. And then we will take the average slope, or the gradient, in 3 dimensions for each of the subsections in the pothole, which is basically the average change in depth of each of the subsections of the pothole. Next, we'll combine the average slope data for each of the 600 potholes into one giant data set of 60,000 values. And this data set can then be statistically analyzed to gather things like the measures of variability and central tendency. So this is some of the code I used to perform that statistical analysis on the set of 3D potholes. And this is the output that I get from this code. So we can see we have 600 different potholes, values that were analyzed. And we get, for example, we can look at this later, but we'll look at the mean for now, which is the average depth of the actual pothole section itself. And we get a value of 61.72 millimeters. And this value will be used later, so keep this in mind. So some basic assumptions must now be made, now that we have our statistical analysis, in order to perform the mock simulation on a real pothole. These assumptions include a Toyota Corolla being used as our subject car, because there are 1.12 million global sales as of 2022, being the best-selling car worldwide, and we will assume that the wheelbase is 1.78 meters, which is the actual wheelbase for a Toyota Corolla, or 1,780 millimeters. We will also assume that the car is a rigid body with no suspension, because incorporating the calculations for suspension would bring the scope of this the calculations beyond the scope of this research project. And finally, we will assume that the pothole sample gathered by the researchers represents the target pothole population that someone implementing this solution in their autonomous navigation system would like to look at. So we should start with this. This is the diagram of a Toyota Corolla, well, a sample car in this case. And we can see A right here represents the wheelbase of the car. B represents the depth that the wheel goes down when hitting the pothole. And we get the angle theta of the whole car as a rigid body that shifts due to the interaction with the pothole. And we relate this angle over to the shift in angle in the image perturbation in the dash cam, which will be mounted up here, and we get theta 2. And so we can perform sample calculations for this using our depth of the pothole as the average 61.72 mean depth of the pothole, and we get a resulting angle of 3.967 degrees, which would be the shift in the angle of the dash cam as the car is driving over the pothole. And we can perform this calculation for each of the 60,000 data set values to get our distribution of angle shifts and image perturbations on the dash cam of the car. So for this, we'll be using a machine learning technique known as the autoencoder. And this will be a custom-built autoencoder built on another researcher's AutoJoy. And autoencoders are self-supervised learning techniques where they turn an input image into a low-dimensional representation, meaning it has much less quality, and then it attempts to recreate the original image from that low-dimensional representation, and it has the original image to reference to, and it learns how to build that data from less data. And these are typically used as denoisers because it is able to build data out of little data, And in this specific scenario, we'll be using this as a denoiser to counteract a specific type of noise, which is the image angle perturbation in dashcam images that results from hitting a pothole. For example, the image, the translation of the image or the actual shift in angle. So the parameters for our autoencoder they're based on a data set of dashcam images provided by Audi and Honda with 850,000 different images and scenarios and steering angles associated with each of them. And we'll be using NVIDIA's pre-trained autonomous navigation model because this solution is to increase the robustness of a pre-trained existing model. And we'll compare NVIDIA's predicted steering angle on an input dashcam image before and after the image perturbation. So we'll produce an image angle for the static image where it should be, and we'll take that as the true steering angle, and then we will translate it with a perturbation and then measure the new steering angle outputted by NVIDIA's autonomous navigation model and measure the difference between the two. And we will optimize the model to have the same steering angle whether or not there are image perturbations, because if the car reacts the same way, whether or not there is a pothole there, then we've increased the robustness of the actual autonomous navigation model. So the tools used for this is that we will use 500,000 images from our set of 850,000 for 50 epochs, meaning that the model will be trained 50 times over this entire set of data. There are a high number of matrix calculations involved in the image manipulation, so we'll be using a desktop with 32 gigabytes of RAM and an NVIDIA GeForce RTX 3090, which is the highest available hardware available at the time for performing this research, which has tensor cores optimized for the matrix calculations used in this kind of operation. And each training cycle still will take 12 hours of continuous runtime, even with this high power of a personal computer. So the evaluation metric we will use is a previously defined loss function known as the AMAI loss. This will combine the average predicted steering angle of the navigation model for each dashcam image, the mean accuracy, meaning how much it aligns with the true steering angle and the image perturbed steering angle, and the improvement, which is the increased degree of robustness in the model over time. We combine these three values and then we get this as our output for the AMAI loss output. And we can see that at the three different checkpoints, the loss output has decreased, meaning the model has performed better and become more robust. We can also see this in the graphs for the training and testing phase, where originally it gave very different steering angle outputs for whether or not whenever the image was perturbed and when it was not perturbed. But then near the end of the training and testing phases, it gave similar results in both the image perturbed and non-perturbed dashcam image inputs. So the goal of this research was originally to develop a model for increasing the robustness of autonomous navigation systems. And from the significant decrease in loss over time seen by our checkpoints in the AMAI loss and the graph, we can say that we have successfully achieved this goal within the scope of this research project. This technique will serve as a backup when there's a pothole collision in case other researchers' avoidance techniques fail, so this will become implemented after the actual avoidance happens. And the cooperative interaction of this with other researchers' methods of pothole avoidance means that this technique does not interfere with their methods of pothole avoidance and only serves as an addition in terms of improving the autonomous navigation model in avoiding potholes or in dealing with potholes for the scholarly work in this conversation. And so the major assumptions used in this research are that the Toyota Corolla was used to represent the average car. So researchers wanting to implement this in their own autonomous navigation system will need to change the wheelbase to match their car. Our car has assumed a rigid body suspension, so the researchers will need to incorporate calculations for the suspension of the other car that they're trying to analyze. And the entire method is only done in simulation, so there's no physical testing. So other researchers should first perform real-world testing on a car before implementing this on their own autonomous navigation systems. And the pothole sample is not representative of a general population of potholes, so researchers should first change the statistical analysis of their potholes to match the distribution of the potholes they're trying to solve their autonomous navigation system for. So the major implications of this solution are that the potential implications are in Tesla's autopilot or other pre-existing self-driving models, and many companies have started using camera-based adaptive steering control systems similar to Tesla's autopilot, so this can be incorporated in many of their systems to increase the robustness of those autonomous navigation systems. And this can researchers for further direction can investigate different types of road deformations, such as speed bumps or different pothole collision situations, such as two potholes together, a very shallow pothole, or other situations like that to improve upon this research and take it in future directions. And physical testing can be done by the researchers on a real car to test the practicality of real-world application of this research, as this was only done in simulation. And these are my sources.
All right, thank you, Shubham. We're going to go ahead and start with oral defense. And Mr. Harris is gonna ask you the first question pertaining to research and the inquiry process.
All right, Sharon, how did the choices you made on designing or implementing your research method impact your research process?
Yeah. So when I was designing my research method, I found a data set online of 600 different potholes known as pothole 600. And this data set only gave me 3 images for each pothole, and I had to manipulate these 3 images to fit a form that would be able to be statistically analyzed. And so I had to then create a method for converting them into 3D objects, and this method was only because of the data representation that was given to me in the pothole sample that I had chosen.
All right, and next up, Mr. Stevenson is gonna ask you a question about depth of understanding.
How do your findings provide directions for future research?
Yeah. So there are many applications, many potential directions for future research for my solution, but the main one is that all the assumptions that I've made were for a specific car, such as the Toyota Corolla or a rigid body car, and these things are not shown in real life. And so if a researcher wanted to implement this solution in a real car, then they would need to change those parameters in my model, and then they would need to shift those to fit their own car, and then they can use that to pursue further research in their own car, or different road anomalies if they want to look at speed bumps or other obstacles in the car and see how to increase their own autonomous navigation systems for those objects in the roadway.
Excellent, and your last question is about reflection throughout the inquiry process. I would like to know, how did your expert advisor facilitate your deeper understanding of the research process?
Sure. So my expert advisor was a professor from my local university, and he helped me a lot, specifically in the statistical analysis portion of my research. So I had the set of 600 different 3D images for the 3D models for the pothole, but then I was slightly lost on how to continue on there from statistical analysis, and he gave me the idea to discretize the potholes into 100 different subsections and analyze the gradient in each subsection and put them into one large data set so I could perform statistical analysis more easily. And that suggestion was greatly helpful in forming the actual statistical analysis, and I ended up using that in my final research.
Great, thank you.